Today, we're going to talk about exponential functions. These are functions that have this kind of form right here, where we have some number, we call that the base, and it's raised to a variable power. And so if we're thinking about something as a function of x, where x's are your inputs, then something like this would be an exponential function. You take a base that is not changing, like 2, and you raise it to a variable power. Similarly, you could have something like, say, 7/3 raised to a power, or a decimal or something like that raised to a power. We could have irrational numbers raised to a power. So if I said, let's say f of x equals pi to the x, then that would be an exponential function. And it's just that its base would happen to be equal to 3.1415, blah, 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 whatever number that is, raised to a variable power. Now, notice this is way different than a different kind of function. Let's say something like this. How about x raised to the 2? These are wildly different. Okay, like for instance, plug in a 1 into this one, you get 2 to the 1 is 2. Plug in a 1 into this one, you get 1 squared is 1. Another thing we'll see is that these exponential functions, well, yeah, we'll get into it, but exponential functions shoot up way faster than, say, something squared or something to the 5th power, or even something to the 10th power. Exponential functions take off, they increase faster than any function like this, right? Of any kind of polynomial. That's a little bit more advanced than what we need to right now. So you could throw that out of your mind if that's too much information, but it's just something to notice that this is way different, right? Like, and I think your book does something like this. Like, this is not the same thing as this. This x, or I'm sorry, 7/3 to the x is way different than x to the 7/3. Okay, and so you might, since we're getting into exponential functions, it's easy to get this stuff backwards and see something like this and go, oh, that's an exponential function. I know how to deal with that. Wait, no. Exponential functions have a constant base raised to a variable power. The things we've been doing before, we have a variable base raised to a constant power. So those are the differences there. We don't want to, we're going on to completely new territory now. And what I'm going to do is we're going to say in general, right? A general exponential function looks like this. We have x inputs, and we're going to take some number a and raise it to the power of x. And so what we usually do is say that a has to be bigger than 0. We're only talking about positive numbers. Now, we can talk about negative numbers. It is possible to have a function like, let's just say, for instance, you could have, let's say, -3 raised to the x. But that's going to be a bit more, the treatment of this is going to be a bit more advanced than what we're ready for. And so the thing is, the reason I'm even bringing this up in the first place is it's not going to be like, it'll be another few more years in your mathematical career before they ever bother to tell you, like, it doesn't have to be a positive number. You can throw in a negative number. You can take a negative number, raise it to a power, and you'll get a perfectly good function. The problem is your outputs are going to be complex numbers. They're going to have the I that pops out. And so that's why it's not really treated. It's kind of like when, for instance, they give you a function like this, g of x equals the square root of, I don't know, how about x minus 1? And they say, what's the domain of this? Would you pause the video right now and see if you could tell me what the domain of this function is? The way we do that is we say, well, the inputs here have to be positive numbers, right? So whatever goes into the square root has to be a positive number. And so x minus 1 has to be bigger than or equal to 0. And so then x has to be bigger than or equal to -1. And you could, I'm sorry, positive 1 has to be bigger than or equal to 1. And you could see that. You plug in a 1, you get a 0. That's perfectly fine. Plug in a 2, 2 minus 1 is a positive number. That's perfectly fine. So we could take any numbers bigger than or equal to +1 and so on and so forth. And then we come along later on in the year and tell you, yeah, you could plug in negative numbers. It's fine. It's kind of like what's going on here, right? Back before, if we said you just can't plug in any negative numbers, and then said, okay, you can plug in negative numbers. It's just that when you do, you get an imaginary output, or you get a complex number with an imaginary part. And it's like, okay, all right. And so now we know, okay, there's a bit more subtlety going on, but nonetheless, we still say, but you know what, we're going to forget about that stuff, except for in some cases. But as far as functions are concerned, we're going to continue to say, no, we're not going to talk about complex values. That's a bit too advanced for us. So for our purposes in our class, we've said the inputs to these as a function has to be positive, and so it has a specific domain. So we're kind of doing the same thing now with exponential functions. We're saying, okay, we're going to require that a is a positive number. And it's not that it can't be negative, it can be. It's just that the thing that pops out when you do that is way more work than we're ready to deal with right now. So just so we're clear, it's not necessary that this is the case, but this is the game we're going to play in this class, that whatever base this is needs to be a positive number. And you might say, well, wait a minute, why couldn't it be 0? Right? What about if it's equal to 0? Kind of like in our previous, the example I just did with x minus 1, it was like, well, it could be 0. You can plug a 0 into that. And so x could be 1 because the square root of 0 is just 0. There's no problems there. And so, well, couldn't we do the same thing here? Let's see what happens when we do. Let's say that we let a be 0. If we said a doesn't have to be strictly bigger than 0, it could be 0. What do we get? Well, we would get a function f of x equals 0 to the x. And what's that? Well, 0 raised to the 1 is 0. 0 raised to the 2 is 0. 0 raised, oh, it's just 0. Well, except for 0 to the 0. Oh, man. Well, now we got something weird because we're not ready to even talk about why that's the case. Turns out that 0 to the 0 is equal to 1, but 0 to any other number, call it k, is equal to 0. And so if we were to graph this thing, it would be, well, 0 everywhere except for right here. And then it would be 1 right here at 0. And it's like, let's just not deal with that. Let's just forget it. Let's just not even talk about that because that is completely different than every other case we're going to talk about. And it's a limiting case too. It's not, you can see why we're not even going to talk about it, right? It's always 0 except for some one weird place. And so who cares, right? It's not really useful for us. So for us in our class, this is what we're going to think of as our general exponential function. And what we want to do now is figure out what these things look like. And pretty much all day today and for your homework, we're just going to be graphing these things to kind of get a handle of what they look like. So let's start with an easy example. And I think 2 to the power of x that's where I want to start. So let's graph that guy. So, okay, we want to graph 2 to the power of x. So I'm going to get my axes here, like that. Here's my x inputs, and we're going to think about this as my y outputs, right? The f of x symbolizes the y outputs, okay? And so let's start by just getting specific values that we could easily calculate. So what I'm thinking is, how about we plug in a 0 And let's plug in a 1, and we'll plug in a 2, and we'll even go all the way up to 3. We also want to see what happens when we plug in negative numbers. So I'm going to go -1 here, -2, -3. Okay. Now you should remember that anything raised to the 0 power is 1. Even 0 raised to the 0 power is 1. And so this is going to be a common theme with all of these, that when we plug in a 0, oh no, I thought my blue was going to work today. Oh well. Let's see if green looks all right. That looks okay. Okay, so f of 0 is the same thing. So remember, what we're doing here is we want to see what the graph of this function looks like. So I'm going to plug in different input values and see what the outputs are. And then I'm going to plot the points. Okay, so I plug in a 0. What do I get? Well, 2 to the 0 is just 1. It's always going to be the case. Anything to the 0 is 1. And so let's go ahead and plot that point right here. There's 1. Okay, now let's go make it bigger first. Let's use the bigger numbers first. So f of 1, you should be able to calculate this one. 2 to the first power just means 2. That's it, 2. Right? Because something to a power of something means we're going to multiply it by itself that many times, or multiply it so that that's how many of them show up, I guess. And so, okay, I plug in a 1, I get out a 2. All right, so I'm going to go ahead and mark that right there. Get a 2. Now what happens when I plug in a 2? All right, plug in a 2, I get 2 to the 2, which is 2 times itself. So there's a total number of 2s. 2 times 2 is 4. And so now, oh boy, it's shooting way up there, and it's looking like I'm going to even run out of space. We'll call this 4 right here. Okay, we'll do one more, and it's certainly going to go off the board now. When I plug in a 3, let's see what I get. Well, 2 to the 3 is 2 times 2 times 2. I have a total of 3 2s. That gives me an 8. And so, yeah, he is literally off the board. He's way up here somewhere. Okay, and so, all right, so we could see what happens. We have some base, all right, plug in a 0, gives me out a 1, and then it shoots up, right? And so, and it's going to keep increasing. And you could imagine, right, the more numbers the bigger numbers you plug in, well, that's just the more times you're multiplying this thing by itself, right? So when we're at 5, we're taking 2 times 2 times 2 times 2 times 2. When you're at 10, it's 2 times 2. 10 times, it just keeps getting bigger and bigger, and it just blows up, right? And so this thing looks something like this. That looks terrible. I didn't do the scale right. You know, it usually shoots way up, way fast, but you get the idea, okay? Now we're going to go in the opposite direction. We're going to go plug in negative numbers and see what we get. So f of -1 says we're going to plug in a -1. The function tells me, okay, I take 2 and raise it to the -1. What does a negative power mean? Well, a negative power, the way I think about it, negative says, take me to the other side of a divide sign. Okay, so take me to the other side of the divide sign. In other words, this, since it's in the numerator, 2, there's a magic numerator that we're not seeing the denominator there, but 2 by itself is equal to 2 over 1. And so 2 to the -1 is equal to 2 to the -1 over 1. And so then that little symbol says, take me into the denominator and then make my sign positive. Or we could even think about it as just flip the sign. So that's 1 over 2 to the 1 is just 1/2. Okay, so he's going to come down as we go back this way. He's going to come down by a factor of, well, he's going to come down to a 1/2. We'd say that as comes down by a factor of 2, right? One thing I wanted to talk about this actually before I went and drew that line, that you'll notice, right? Like this has a, when we plug in integers, it has a very concrete, there's a concrete idea that goes into your head. Like for instance, when I plugged in a 3, I got 2 to the 3, which means 2 times 2 times 2. And I can literally calculate that out and get a number, right? And so when I plug in a 1, that just means 2 to the 1. It just means, well, I have 1, 2. It's just 2. But what about like halfway between there? What if I plugged in say a 1/2? What would that be? Well, 2 to the 1/2. Well, if you remember from when we were talking about radicals and fractional exponents, this is the same thing as the square root of 2, right? And we talked about why that has to be the case, to make everything nice and consistent. We want the rules of dealing with exponents to be consistent, whether or not they're integers or if they're rational numbers and whatnot. Similarly, it's like, and if you were to calculate this thing, this number turns out to be 1.414 or something. And yeah, it's between 1 and 2. And so, yeah, we have that point there. And we could go on and fill this in with a bunch of different fractions. And so, like, for instance, if we had 3/4, we want to plug in a 3/4. We say, well, that's the same thing as, and I could see this in a couple different ways. That's either the 4th root of 2 to the 3rd, or we could think about that as the 4th root of 2 raised to the 3, right? Remember our rules for rational exponents is that we could do that in either order. And there are ways of calculating what this number would be, and then we could take that number and raise it to the 3rd and so forth. And if you did that, you'd end up with a bunch of points here. The thing is, what we're missing are all the irrational numbers. Like for instance, the square root of 2 itself is irrational. You can't write it as like say 3/4 or some integer over another integer. And so we have this thing living right here, the square root of 2, which is approximately 1.414 blah, 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 blah. You can't write that as a fraction. So what do we do with that? Well, this is more on the theoretical side of what's going on, and your book actually talks about it. I was surprised. What we could do is basically we could define this thing as the limit of a sequence. This won't be too important, but I want to bring this up just to be complete about this. We could say if we're trying to figure out what 2 raised to the square root of 2 is, we say, well, that's the same thing as 2 to the 1.414 blah, 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 blah. And what we could do is say, well, this number right here, whatever it is, we could approximate whatever that number is by plugging in better and by getting numbers that get closer and closer to the square root of 2 and plugging them in. Like for instance, we could say, well, what if I just raise 2 to the 1.4? You say, well, I don't know how to do that. Well, we could rewrite that as 2 to the 14/10. Okay, and so that's 2 to the, I guess we could put the 14th root of 2 raised to the 10th power, and we could plug that into our calculator. Actually, our calculator will just do this. It could actually just do that. In fact, our calculator would just do this. But theoretically, how can we justify what we're doing here when I draw that line to connect all these points together? Can I do that? And it's like, yeah, actually we can, and this is how we do it. This is the justification, is that theoretically we've defined what this is. We'd say 2 raised to the 1.4 is the same as 2 to the 14/10, which is this beast right here. So we plug that in. We take our 1.4 right here, plug it into our function, and we get out some number here. Then we say, okay, well, we're trying to approximate this. So let's get even closer to that number. So we say, okay, 2.141. We'll plug that in and see what we get out. And that gives us 2.141 over 100, which is, I guess, the 100th root of 2. Oh, look at what I did. I did that wrong. Did you catch me? You better have caught me. Look at that. I said the 10th, that should be the 10th root, raised to the 14th power. This is the 100th root of 2 raised to the 141, which we plug into our calculator, we find some output, and it will be even closer to something. And I'm going to kind of zoom in right here to show you what I'm doing. That if we zoomed in on this little bit right here, we said, okay, let's see what's going on. What are you doing here? Well, you're plugging in these different values. 1.4. The next one would be 1.41. The next one, and you can see actually, the more digits I do, in fact, we're zoom in even more. So to make this nice, we'll say 1.41 is here. And what's even closer to it is 1.414. And what's even closer to that is the next one and the next one. And until we're approaching that number, the square root of 2. We plug that in and we get some output. How high do I draw it? Well, however high it is, right? I guess it works out to, you could plug this in. It would be a good exercise to go get a calculator right now. You could pause this and do it. Get a calculator, punch in 2, and then the little caret symbol, which is raised to the, and then do 1.4 and see what you get. You get some output value. And then you go, okay, well, now let's raise it to raised to the 1.41, which is what we do here. And we get some other output value. And you keep doing that with the next bits and the next bits. And all of these approach some value. They're going to get closer and closer and closer. And that's kind of what we're doing here with all the irrational numbers. It's how we can justify drawing a straight line here. Because what did I do? It's not a straight line, I'm sorry. Drawing a curve between all these points. Because if you really think about it, if you want to be if you want to be a pain in your teacher's neck, you could say, well, wait a minute. You started with a dot here, and a dot here. How do I know I could just connect them? And you could say, well, we know how to throw in the rational numbers. We've talked about that before. 2 to the 1/2 means the square root of 2. Oh, okay. And the same thing with the 2 raised to the 3/4. We could talk about that. But what about all those irrational numbers? How are you going to compute that? This is actually getting into something pretty deep in mathematics that some people take issue with. Not everybody's on board with this, but the idea is we can define sequences and say, well, if you have an irrational number, some decimal that doesn't terminate, doesn't repeat, you could plug in better and better approximations, and you will get closer and closer to a value. And so that's what we're doing. And we're going to say, well, then if you wanted to be a jerk and be like, well, we only know all of these rational numbers that we could plug in. So what about all of the points that we've missed? And we could say, well, you just get a closer and closer approximation, and you will be getting closer and closer to whatever it is when you take 2 times the square root of 2. And whatever that is, we'll just say, well, then that's the value. And if you really wanted to, you could play with this and see that these numbers do all occur on a curve. They don't jump up all of a sudden and, jump down, but they're all continuous, right? That you go from one to the next, and so on and so forth. So as way more information than you want, and then it's even useful. Your book kind of talks about it, and it is I want to try to be as complete as I can when talking about this stuff. Yeah, so sorry. So between -1 and 1, we're just going to connect all the dots, right? We could assume like, yeah, it's not going to jump up out of anywhere. And if you plug in a bunch of numbers in between it, you'll see like, yeah, you plug in a number just a little smaller than 0 and you get something just a little smaller than 1. Plug in something a little bit smaller than that, you get something a little bit smaller, and you get a bunch of points that all lie on a curve like that. So that's what we're doing when we draw the line. That's the theoretical justification for why you could do that. But yeah, sorry. So let's continue with our points. We want to plug in a -2. We plug in a -2. F of -2 is 2 to the -2. Now we say, okay, 2 to a negative power, any number to a negative power means flip me, okay, put me on the opposite side of a divide sign, and then flip my sign. So that's 1 over 2 to the 2. 2 to the 2 is 4, so that's 1 over 4. And so again, we take that height. So before when we were at 0, we were up here at 1, and then we halved the height. Now we're at a half, we're going to take, again, 1/2 of that height to get down to 1/4. When we plug in a 3, what do we get? 2 to the -3. That's 1 over 2 to the 3, which is 1 over 8. And so we half that distance again. 1/2 of a quarter is 1/8, and so we've dropped down to a half. Okay, and that's what that thing looks like, and it keeps halving that distance. And you'll notice that when we go in the opposite direction, it kind of doubles the distance, right? When we were at 0, we're up at 1. We move over to 1, the distance doubled. We went up to 2. Move over to 2, the distance doubled. Now we're up at 4, right? We move over again, the distance doubles, and we're up at 8. If we went to, I think I said 4, I meant 3. When we go over to 4, that distance is going to double. It's going to go up to, and it's going to increase by, every time it's going to be, well, it kind of makes sense, multiplied by this factor right here. Why is it doubled? Well, because every time you move 1 unit this way, you multiply by an additional 2. So whatever height you're at, you move over more, you're multiplying by 2, it should double that height. And so that's what we're seeing right here, right? And then moving in the opposite direction, moving in the negative direction, well, it's basically the same game. It's just like now the base, which is 2, is in the denominator. And so we go left 1 unit, and now we have a 1, 2 in the denominator. We move left 2 units, and we have 2 2s in the denominator. So that's like taking, this one takes half, and then we go over and half that distance. And every single time we're just kind of throwing on 1 more 2 in the denominator, in effect, just decreasing by a half, or we're halving the distance each time, decreasing by a factor of 2. Now we have an exponential function whose base is a number that is less than 1. Let's just see what happens. We're just going to plug. We're not going to talk too much about this. We're just going to plug in numbers and see what happens. I've already done the first one. When you plug in a 0, anything, I don't care what it is, raised to the 0 is 1. And so a 1 pops out. In this case, it happened to be 1/2 raised to the 0, and we got out a 1. Now let's plug in a 1. Well, this one's also very easy. Anything raised to the 1 is just whatever that thing is. In this case, it's 1/2. And so it drops down by a factor of 2, or the distance gets halved. Guess what's going to happen when we plug in a 2? Well, we get 1/2 squared, which is 1/2 times 1/2. Which is the same thing as 1, because 1 times 1 is 1. 2 times 2 is, well, 2 squared, or how about 1/4? Does this look familiar? Seems like we just did this. So it drops down again by a factor of 2. Or we could also think about it as we half the distance every time. Guess what's going to happen when we plug in a 3? 1/2 to the third is the same thing as a half times a half times a half. We're just multiplying this base by itself 3 times. And we could see that since this number is less than 1, every time we do that, it gets smaller and smaller. And we end up with 1/8 because that's 1 over 2 times 2 times 2, 1 over 8. And again, we've halved that distance. And now we're down here at 1/8. Okay. And without going into the long, boring conversation about sequences and all that, we could say, okay, then this thing, every number in between those integers are going to fall on a curve, a nice continuous curve. It's not going to jump up out of nowhere or anything like that. It's going to continue to have this shape. Okay. Now for the fun part, let's plug in some negative numbers. Okay. So I'm going to plug in a -1. There's a couple of ways we could think about this. 1/2 raised to the -1. Okay. We could say, well, just like we did before, anything raised to a negative power is 1 over that thing, but now raised to a positive power. And so this turns out to be 1/2. I'm sorry, 1 over 1/2 raised to the first, which is the same thing as 1 over a half. But divide by a fraction is the same thing as multiply by the reciprocal. Okay. We have 1 times 2 over 1. It just comes out to 2. Convince yourself of that. Convince yourself of that. Another thing, but another way we could look at this is if we had any fraction, let's just say a over b raised to the -1, we could say that's the same thing as 1 over that thing raised to the first power, a over b. And then we play the same kind of trick. We say, oh, you take 1, divide by a fraction. That's the same thing as multiplying by the reciprocal. That's b over a, like that. And so it's just b over a. And so that's another way. If you have a fraction, you could just say, well, wait a minute, that just means flip that guy, right? And I think we've talked about this before, right? And let's just use, how about, we'll do a over b again, but let's raise it to the -3rd. If we wanted to, we could do it this way, where we say, okay, 1 over some negative power means bring me into the denominator and make me positive. Doesn't matter what that thing is. That's just an a over b. So it's just an a over b. Okay. To the 3rd power, well, that means, let's just use some more space right here. A over b to the 3rd power means a over b times a over b times a over b. That's just a to the 3rd over b to the 3rd, right? That's what that means. So I could say, okay, a to the 3rd over b to the 3rd. But we're dividing by a fraction. So that's the same thing as multiplying by the reciprocal, right? That's a 1. I'm not even going to bother with a 1 this time. We just have a 1 on top. Then a b cubed over a cubed is what I'm left with right there. And yeah, that's kind of what we're seeing right here. It's just that, right? It's like as though I just flipped the fraction. When you have a fraction raised to a negative exponent, you could just flip the fraction. And since it's 1 over 2, well, that's just 2 over 1. Oh yeah, 2 over 1 is just 2. A over b to the -3rd, we could think about that as saying, well, just flip the fraction and then make that positive. So a couple ways of dealing with this as you go to mess with these and get actual values. Save yourself a little bit of time if you remember, oh, a fraction raised to a negative power is the same as just flipping the fraction and then raising it to that power. So, but let's see what we found. We plugged in a -1 into here. 1/2 to the -1 is +2. Okay, so I'm going to draw that right here. There's 2. Okay. Now, what's going to happen when we plug in a -2? Well, 1/2 -2. Could drop it, or I could flip it. This time I'll flip it. I'll just say, okay, that's the same thing as 2 over 1 to the positive 2, which is 2 over 1 times 2 over 1, which is 4 over 1, or how about just 4? Convince yourself of that, right? I did it differently than I did it last time. But when we plug in a -2, we get out a positive 4. And so we're way up here now. Okay, and that's 4. Plugging in a -3, you get F. -3 is the same thing as 1/2 to the -3. And I'll do it the first way this time, just to kind of show. We could do it either way, whatever way you're more comfortable with. Negative means drop it into the denominator, make it positive. Okay, what was it? I guess it was 1/2. 1/2 cubed is the same thing as 1 cubed over 2 cubed, which is 1 over 8, right? So that's 1 over 8, which I could flip back up as just 8. Being a bit more explicit there, just to make sure we're on the same page. This is the same thing as 1 over 1/2 times 1/2 times 1/2 is 1 over 8. Divide by a fraction is the same as multiply by the reciprocal. 8 times 1 divided by 1 is just 8. And so, yeah, we get 8 right there. And so this shoots way off up here, right? We're going to double that distance again. And so it's way out of there. And I'm going to go ahead and connect all these guys with a nice curve like that. And so what are we seeing here? Well, I said this a second ago. When we have a base that's bigger than 1, it shoots up this way. When we have a base that's smaller than 1, it shoots down like this, or rather, we call this decay. In particular, it's called exponential decay. All right, so we have exponential growth when it shoots up. This is called exponential decay this way. And so, okay, I want to take a minute and prove why this is the case in general. So let's do the case that's on the board right now, where we have a base that is less than 1. And so we're thinking about a function that looks like this. We'll call it g of x equals a to the x. And so this is very similar to this. And it's in this case, the a, which is the base, is less than 1. Okay. So if a is less than 1, then let's see what happens to this thing as we start multiplying it by itself, right? Because that's what you do when you're plugging in integers into there, right? You plug in a 2, it says multiply this thing by itself 2 times. You plug in a 3, multiply that thing by itself so that you have a total of 3 of them, and so on and so forth, right? So let's do that right here. A is less than 1. I'm kind of thinking, I kind of want to do this simultaneously with this one so that you could believe what I'm doing. So this isn't just symbols. This is kind of like what I'm saying here, right? Like you have some number that is less than 1. For instance, 1/2 is less than 1, right? Okay, so what I'm going to do is multiply both sides of this equation by a. Like I said before, we're taking only positive values for a. We're never going to take negative values for a. So we don't need to worry about, wait, do I need to flip the inequality or anything like that? Because we're certain that a is a positive number, okay? As a matter of fact, let's just go ahead and do that right there. So we're even going to be explicit in the way that we line this up and say, not only is a less than 1, but it's also bigger than 0. So to kind of go with this example, we're saying we have a base, 1/2. It happens to be less than 1. And of course, it's bigger than 0 because that's what we're talking about in this class. So what I'm going to do here with this first equation I'm going to go ahead and multiply every one of these things across by a. Okay, so I'll have a times 0 should be less than a times a, which is less than a times 1 right there. A times 0 is 0. A times a is a squared. A times 1 is just a. And what was our very first thing we said is that a itself has to be less than 1. Okay, so a is less than 1. And you see what's happening here, right? It's we once we multiplied a by itself, the number we got is smaller. Let's make that concrete by doing this over here. Okay. In this case, we're going to be multiplying 1/2 by itself. And I claim it just keeps getting smaller as we go. And so let's do that here. Let's take this entire inequality, multiply it through by 1/2. That'll be 1/2 times 0 is less than 1/2 times 1/2, which is less than 1/2 times 1. So I just took an inequality, multiplied all the way across by a number. So 0 times anything is 0. 1/2 times 1/2 is 1/4. 1/2 times 1 is 1/2. And that 1/2 is less than 1. If we weren't certain about that, we could look back and go, oh yeah, no, that's right. That's what we started with. 1/2 is less than 1. All right. We'll just do this one more time. And I think you see how this works, right? If I then say, okay, well, now I have this, what happens if I go through and multiply everybody through by a again? That's a little bit more room here. Well, I would have a times 0 is less than a times a squared, which is less than a times a. Multiplying this guy right here, I have a times 1. A times 0 is a big fat 0. A times a squared is a cubed. I have a total of 3 a's right there. A times a is a squared. A times 1 is a. And we said at the beginning, a is less than 1. And that is what we're seeing in this, right? We're seeing this as well. That the a that you started with is less than 1. And then when you square it, it gets smaller. Then when you multiply it by a again, or when you cube it, it gets even smaller, and it keeps getting smaller and smaller and smaller. We'll do it one more time with this one, just to kind of tie everything up, right? If I take the original base that I had and multiply this inequality by it, I get 1/2 times 0 is less than 1/2 times 1/4 is less than 1/2 times 1/2 is less than 1/2 times 1. The 0 makes that a 0. 1/2 times 1/4 is 1 over 2 times 4. 2 times 4 is 8. 1/2 times 1/2 is 1 over 2 times 2, or 1 over 4. 1/2 times 1 is just 1/2. And we know that 1/2 is less than 1. And sure enough, that's what we're getting, right? We're seeing that when you have a base that is between 0 and 1, as you keep successively multiplying it by itself, this number keeps getting smaller and smaller. And that's what we found by actually just doing the calculation, right? So that the bigger numbers you plug into here means that's the more times you're multiplying this number by itself, which means it's going to keep getting smaller and smaller. But I don't think I need to continue this with the 4th power and the 5th power and the 6th power and so on and so on. I think you should probably believe that this trend continues as long as you want, because I could keep making this argument. I could just keep doing this, multiplying the entire thing through by a to eventually get this is less than a to the 100, which is bigger than, which is less than this, which is less than to the 98, and so on, all the way to a, all the way to 1. And so we're seeing that when you have a base that is less than 1, if you go in this direction, right, as you go into the positive x direction, effectively what you're doing is multiplying that base by itself over and over and over again. And we can see that that's going to continue to get smaller and smaller and smaller. Another thing we could see, because I added that 0 in there, is that it'll never actually get to 0, right? Like, I could keep doing this forever. I'm here at a is 100, and it's still going to be bigger than 0. There's no way, and think about it, right? A half times a half times a half times a half. Do that forever, and then a day, and you're still going to have a number that's bigger than 0. It'll be a tiny little number. It'll be 1 over 2 to the billion, but it still never quite gets to 0, right? And so that's what we're seeing here in this graph. This is graphically how we represent this fact right here. And remember, it was that a is a number that's less than 1 and of course bigger than 0. That's my base that I'm dealing with right here. And so the overall shape this is going to have is that it's going to come down this way. And then we could like reason by analogy. Well, then, yeah, then when you plug in negative numbers, that's just 1 over that number. And so if you have something that's less than that, right, you have 1 over a half, right? So like 1/2 raised to, let's say, the -10. Well, you're raising it to a negative power. And so that just flips the fraction, right? Like we talked about before. That's the same as 2 over 1. And now when you flip a fraction, well, you just made that number bigger than 1, right? And so now when you start multiplying it by itself, it gets bigger and bigger. And that's why it shoots up in that direction. So we just saw that when a is between 0 and 1, or we're just going to think about that as a is less than 1, that's my base, then a squared is less than a, and a cubed is less than that, and so on and so on and so on. A to the n is less than all of those, and then we can keep going and keep going, and it's always going to be bigger than 0, right? We're just saying this is a fancy way of writing this phenomenon right here. And what I said a second ago is, well, then of course, when you make it negative, it's bigger. Let's be a little bit more explicit about that. I claim, this is my claim, that when we take a and we raise it to a negative number, like -2 or -3, or let's just call it -n, right? Any one of those, -n. My claim is that that number is actually bigger than 1. Let's see if that's the case. Not sure, but that's my claim. Someone say, is that true? I don't know. How could I show that that's true? Well, first off, I don't like negative exponents. So let me just rewrite this thing that I'm trying to prove here as, how about 1 over a to the positive n? And I'm asking, is that less than 1? Is that true? I still don't know. I'm not sure at all. I do know it's a positive number. I mean, a to the n is a positive number because we said that a is a positive number. So any power of that guy is going to be a positive number. Okay. And so I could multiply both sides of that equation by it, and it's not going to flip the fraction. So let's do that. I'm going to multiply both sides by a to the n. That cancels that guy, and I get 1 on that side. On the left-hand side, I have 1. I'm asking myself, is this true? 1 times a to the n, a to the n. Is that true? Yeah. That's, in fact, that's what we just showed, right? The bigger power you take, right, the smaller and smaller it gets, but it's always going to be smaller than 1. So to make this a bit more formal, we could just kind of go in the reverse order here and say, okay, I feel confident about this. So I'm going to go ahead and start with something we know. It is the case that 1 is bigger than a to the n because of what we talked about before. It is the case that, and I'm sorry I did it this way, but we'll write it the other way, that it is true. This right here implies that 1 is bigger than a to the n. Therefore, I could divide both sides by a to the n. I'm going to go ahead and do that, a to the n. I have 1 over a to the n is bigger than 1. But I could rewrite a to the n as a to the negative n. And we can say that is bigger than 1. And if we wanted to mess with this a little bit more, we could do this with, say, like a and a squared and see that, yeah, even the further you go that way, the higher up it has to go. I kind of wanted to formalize this and say, yeah, okay, so then whenever a, and we can and we can see it easily, like I'm being really abstract here with the a's and stuff like that, but this is trivial when we go to do this with an actual number. Like, let's do it with an actual number to just see what I've been trying to illustrate here. We said, well, I claim that that's true whenever a is less than 1 and bigger than 0. So let's just see. I claim that 1/2 raised to the negative nth power is a number that's bigger than 1. And I'll just do it the same way I did. I'll say, well, I don't like negative power, so I'll rewrite that as 1 over 1/2 to the n, like that, positive 1. And I say, is that bigger than 1? Well, what is 1 divided by a fraction? Well, hold up. Let's just be really careful here. 1 over, how about 1 to the n over 2 to the n, like that, bigger than 1. Yeah, and 1 divided by a fraction is the same thing as multiplied by the reciprocal. So we have 1 times 2 to the n over 1 to the n. Is that bigger than 1? Yeah, it definitely is, right? And we could just forget about that 1 down there. We have 2 to the n is clearly bigger than 1. And that's what we're seeing here. In fact, it's like the old function we had, 2 to the x, the first function we dealt with, only it's kind of in reverse, right? As we go that way, now we get, when we plug in a -1, we get out the +2. Plug in a -2, we get out the +4. So before, when we were talking about how modifying f of x changes the graph of a function, we said that if you take a given function f of x and you multiply it by -1, or we can just write that as negative f of x, and what that does is it flips the graph of the function over the x-axis. We call that a reflection about the x-axis. And it'll be good to go through this to see why this is the case for what we're about to do. So now you'll notice I don't have a actual formula for this function written down. But what I can do here is just look at this and say, well, this means a couple things. I know that in this case, when I plug in let's just start over here at 2. When I plug in a 2 into f, I get out a 0. So the output value is 0. I know that when I plug in a 1, the output value is a 3. Once you finish this up, figure out what f of 0, f of -1, and f of -2 are. So go ahead and pause the video and figure out those last 3 points right now. You should have gotten that you plug in a 0, you get out a 2. You plug in a -1, you get out a +1. And you plug in a -2, you get out a +2. And so then the thing that we're trying to draw here, right, or the thing that we're playing with now is negative that. We're going to take, if you think about that, as taking -1 times that value right there. And so I'm just going to do that to both sides. I go negative, I get a negative over here. That's just, well, -0 is just a 0. Negative f of 1 is -3. Negative f of 0 is -2. Negative that is negative that. Negative that is negative that. And so we could, now let's just plot these points and see where they end up. You get this. So there's -1, there's -2, and there's -3. Okay, so if we're talking about this new function, negative f of x, when I plug in the 2, I still get out a 0, so that hasn't changed. Plug in the 1, now instead of going up to -3, the function right here tells me, well, no, you go down to -3. I think I said up to -3. And instead of going up to +3, you go down to -3. Now, when I plug in a 0, I used to get out a +2. Now it says just flip it, reflect it, go down to -2. Okay, so it goes through here at -2. It used to be the case I plug in a -1 and I got out a 1. Now it says take that and make it negative. So it flips it down to -1. Finally, it used to be I plug in a -2, I get out a +2, but now we're saying just take that, make it negative, and so it flips it down to -2 like this. And if we were so inclined, we could go through and find every single one of these points if that were the point of all of this, but I'm not trying to be too accurate. I'm just trying to get a general idea of what this looks like. And I could see that, yeah, this point right here would get reflected down to here. This point right here, multiplying it by -1 would reflect it down to here. And I could continue this entire thing like this and say, that is what negative f of x should look like. Now the question is this. We didn't talk about this before. We want to know what happens when you make the input negative. When you make the output negative, it's pretty easy to deal with because you're saying, well, if your output is just a height up or down, you're going to take that value and then just make it negative. It's just going to flip over. Right. And so if it had started below the x-axis, it's just going to flip up above the x-axis and vice versa. Right. But now what we want to do is see what happens when we multiply the input by -1. And what do you guess that's going to do? Well, let's figure this out. And it's going to be a little bit, we're going to be a little bit more delicate about this than we did with the negative f of x. What I'm going to do is this. I'm going to say, okay, this is the thing we want to graph right now. So let's give that a new function name. Okay, let's call it g. We're going to say, okay, g of x. Okay. And we're only really given 1, 2, 3, 4, 5 input values that we actually know the outputs for. So let's do those kind of the way we did before. Okay. This says, okay. And we'll start on the same side. We'll start with the positives. We'll say, okay, when I plug in a 2, this says to take the input and make it negative. All right, so now when g is over here at +2, say, okay, we plug in the +2, and then this says take that input value and make it negative. Okay, and so it says then it's f of -2. Well, what's f of -2? Well, I'd have to look over here and see. Say f of -2 is equal to +2. Okay. Okay. It's almost as though we swapped these two guys. We had a 2 over here. It's like it just got swapped down to -2. Let's see. Let's see if that makes sense. Now, G says when I plug in a 1, what do? Well, by definition, whatever I plug in here, I just plug in right there. The only difference is I make it negative. So instead of a +1, it's now a -1. What is f of -1? Well, I don't know. Let's see. Plug in a -1 into f, and it says my output is +1. Okay. And again, it's as though when I'm over here at G, when I'm here, it's like it's telling me to take the value of f from here. It's as though we're taking those two values and we're swapping them. Interesting thing happens here at 0. Plug in a 0 into G, my new function that I'm trying to graph. And it says, okay, you take that input and make it negative. Oh, but a -0 is just a 0, so I don't need to worry about it. I just plug in what I got at 0. F of 0 is +2. And so, okay, that didn't change. I was at 0. It stayed put, right? We got the same thing here. Now, I would like for you to finish this off. You compute, what do you get for -1, g of -1, and g of -2. Pause the video and figure that out. Okay, so g of -1, I plug in a -1 and I get a -1, right? It says take x and make it negative. And so I take a -1, make it negative. Well, that's the same thing as a +1. So it's the same thing as f of 1. All right. And then what do? Well, I don't know what it is, so I'm going to have to plug in f of 1. I go to f, plug in a 1, and I get out of 3. Go. Okay, g of -2. I take -2 and plug it into here. That's a -2. -2 is a +2. F of 2 was a 0. There we go. Okay, so let's graph this guy and we can see what's happening. We should be able to see what's happening. And I already said, it's like we're going to the opposite side, right? When we're over here at 2, it's as though we're at -2. When we're at 1, it's as though we're at -1. At 0, it stayed put. At -1, we're at 1, and so on and so forth. And so it's really what I'm expecting is that it's just going to flip again. It's going to reflect this thing, but in this case, it's going to reflect it around the y-axis. Let's see if that's the case. So when I plug in a 2, I get out a 2 for g, my green function. When I plug in a 1, I get out a 1. Plug in a 1, get out a 1. Plug in a 0, I get out a 2. So I plug in a 0, I get out a 2 right there. Okay, plug in a -1, I get out a 3. Plug in a -1, get out a 3. So I'm up here. Finally, plug in a -2, I get out a 0. Plug in the -2, get out the 0. And yeah, it's quite literally the same thing, but in the reverse order, right? This is exactly what this has done. By making the input negative, this thing is a reflection. This time it's about the y-axis. We've taken this thing and whipped him around this way so that we go up and back, up like that. And it's kind of hard to see. It looks like McDonald's now, but like that's what we've done. We've just taken the original picture, the black function, and we've flipped it around to get the green function. And that is the effect of multiplying an input by -1. And it kind of goes along with everything we've been saying. You mess with the x values, right? And it does something to the x values. You mess with the input values and it messes with your x-axis. You mess with the output values. You take your output, f of x, or we could even think about that as y, and it messes with your y values. Continuing on with that line of reasoning, let's suppose that we had the first exponential function we worked with, f of x is equal to 2 raised to the power of x, or 2 to the x, right? And we've seen before that this thing increases, that when you plug in a 1, you get out a 2. Oops. Yeah, plug in a 2, you get out a 4, and so on and so forth. It goes up and up and up that way. And then when you plug in negative numbers, it's like 1/2, and so it jumps down to a half here at -1. You plug in a -2, you get out 1/4. So this is what we've done before. Now, if I wanted to draw a new function, g of x, and I said g of x is just going to be f of -x, I could do the same thing I did before and say, wait a second, if you made the input negative, that's just going to flip about the y-axis. It should just be a reflection. And I could reflect this exactly. And I don't need to use my brain. I don't need to plug in a bunch of things like we just did. I'm just going to use that fact from now on and say, well, make your input negative. It should flip this guy around. And so, well, one point's not going to change, and it's going to be the point that's right here, I mean, that's the place where we are reflecting it right there. We're reflecting about the y-axis. So whatever's on the y-axis isn't going to move. But now this point that's up here at 2 is going to get flipped around and show up here, right? This point that's up here at 4, he's going to get flipped around and show up at 4 down here. So it used to be you go over 1 up the 2. Now you go back the opposite way and you go up the 2. It used to be you go over 2, you go up the 4. Now it's just flipped around. You go down to -2, you get up to 4. And these other points are going to get flipped around. The one that's over here at -1 1/2, he's going to get flipped around. And it's the same distance right there. He gets flipped and ends up that distance away at the same height. So at 1, he's at 1/2. At -2, this one's that's at -2, he's going to get flipped around and end up here at +2 at the same height. They're at 1/4. And we could just connect the dots basically because, right, like it's a nice continuous line. This entire line that's here is just going to get flipped around and show up right there. And so it's going to look like that. And this is going to look terrible because I'm doing this from an angle. But anyway, that's the idea. Does this look familiar to you? Is this something maybe we've graphed before? Well, let's see what this thing is. Okay. G of x equals f of -x. But f of x is 2 to the x. And so if I plug in a -x there, I would have a -x right there. -x, like that. You go, okay, and what's different about that? How do we deal with negative exponents? Take this thing, say, wait, negative exponent means bring me into the denominator. Okay, so that's the same thing as 1/2 to, now we make that positive 1/2 to the x. Let me say, wait a second. That's the exact same thing as 1/2 raised to the power of x. Right there, isn't it? Check me on that. Am I wrong? I don't think so, right? Like 1/2 to any power, I don't care what it is, 1/2 times 1/2 a bunch of times. You're always just going to get a 1 in the numerator. And then your 2 is going to be, well, 2 to whatever power this is, 2 to the n. That's the exact same thing as 1/2 to the n. So these things are exactly the same, right? And so that's cool. I think that's pretty cool that it's consistent, that we could think about this geometrically. Or if you're not comfortable with that, you could just plug and chug and stuff like that. But it's going to be good for you to be able to do this both ways. You will want to be able to justify something both ways and say, well, wait a second, this is the same thing as that. And so, okay, like I'm sorry, this right here is the same thing as that. So I could think about this as, what are my rules for the base? When the base is less than 1, it's a decay, right? And that's what we talked about with all those a's and raising them to different powers. And well, this base is bigger than 1. But it's to a negative power. So a negative power brings it into the denominator. And since that's bigger than 1, that thing has to be less than 1. Right? It's easy to see when you're using actual numbers like 2. Like you could see, well, yeah, 2 is bigger than 1. And so then 1/2 is less than 1. Right? It's a little bit more abstract with the a's and stuff like that I was using. But I hope this all kind of makes sense why this is the case. Just to be complete, I want to do this and show that that if your base is bigger than 1, your thing is going to blow up. It's going to get bigger and bigger. And we're going to do this the same way. I have that 1 is less than a. So if I multiply both sides by a, I get that a is less than a squared. But we just said that a is bigger than 1. So, okay, like that. Okay, cool. same thing's going to happen, right? I multiply everybody through by a. A times 1 is less than a times a is less than a times a squared. That gives me a times 1 is a. A times a is a squared. A times a squared is a cubed. And we know from the very first assumption that this thing is 1. And so this brings us to our big picture that we're trying to develop. We want to, like I said, most of these exponential functions, they're slight differences in very, very few things, like if you've taken it and you've shifted it and stuff like that. But if you're just talking about some function, f of x equals a to the x, and you're not like making it a negative x, right? Or you're not like shifting it up or down or anything like that. It's going to look, there's going to be two different pictures. That if a is bigger than 1, this thing is going to shoot up. Why is that? Well, because of this thing right here. When you plug in a 1, you have your a, which is already bigger than 1. Rather, we should start by saying, when you plug in a 0, you get out a 1. That's always going to be the case. Always, always, always going to be the case. F of 0, in this case, a to the 0 is 1. And then it's like, well, then when I plug in a 1, is it going to get bigger or smaller? Well, is a bigger than 1? Yeah. So then a to the 1 is a. Yeah. And a is bigger than 1? Yeah. So it's going to need to be bigger up here, right? It's going to need to increase. And then we just have this type of thing. And it's like, well, then by the time you square it, it'll be even bigger. Like 2 times 2 is bigger than 2. So it gets bigger. And then do that again, multiply it again by a number bigger than 1. It keeps getting bigger and bigger and bigger. So this is what the curve is going to look like when a is bigger than 1. Said that backwards, when 1 is less than a, but you see what I'm saying. I like to think about it as a big a, when a is bigger than 1. However, if a is less than 1, it just does the opposite thing, right? If a is a smaller number, if it's between 0 and 1, then every time you multiply it by itself, it's going to get smaller and smaller. And so you could say, again, well, when you plug in a 1, what do you get? A. A to the 1 is a. And so, okay, is a smaller than 1? Well, yeah, that's what we just said. Okay, so then it has to come down, right? No way around that. Keep multiplying it by itself. It's like the opposite of this is the first one we did, that long chain. They just keep getting smaller and smaller and smaller and smaller. And so your picture is going to look like this. Still goes through 1. It's always going to go through 1. It'll never not go through 1. And then it decays like that. This is the case where a is less than 1. We didn't talk about what happens when a is equal to 1, because that's a stupid function. Like it's even worse than 0 to the x, right? Like if you're talking about this function right here, f of x equals 1 to the x. First off, why are you talking about that function? Like it's always going to be 1. It's just going to be a constant, always, always, always constant, right? Plug in a 0, you get out a 1. Plug in a 1, you get out a 1. Plug in a 2, you get out a 1. It's just a straight line, right? And so these are basically, this is all you need to know right now for graphing exponential functions. This is where you're going to start. They're either going to look like, they're either going to shoot up if your base is bigger than 1, or they're going to come down if your base is less than 1. Right now, we are graphing the function f of x equals a to the x. And right now, a is equal to 1. And like I said, it's the most boring function. It's just 1 all the time. It never changes. Watch what happens when we make a bigger than 1. Oh, what did it do? Well, you say, well, man, I'm going to have to really work on and look at what number it is, because when it's just barely bigger than 1, it's really flat and blah, 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 blah. Well, no, if you zoom out far enough, this looks exactly like the thing I've been drawing on the board. We will not be too concerned with scale here. Everything should basically look like this. And so what I'm getting at with this is whenever your A is bigger than 1, yeah, the bigger that A gets, the faster it shoots up, right? Like 9 squared is way bigger than 2 squared, right? But it generally looks like this. It shoots up. And where does it go through? Oh, what do you know? It goes through the y-axis at 1. There's no way around that, right? I don't care how big or how small this number is, it's got to go through 1. And so then, okay, we're coming back down to where A is equal to 1. We're at 1. And when I drag A down, yep, A is less than 1. And so it has that decay, right? It starts high, goes through at 1. That never changes. And then it starts to decay, right? And if I get 0.5 here, there's 0.5. There you go. That's the guy that we were working with earlier. Why? Because 0.5 raised to the x, which is what we're graphing right here, is the same thing as 1/2 raised to the x. You plug in a 0, you get out a 1. Plug in a -1, and you should get out a 2. Yeah, there you go. Plug in a 1, you should get out a 1/2. And right there, yep. Plug in a 2, you should get out a 1/4. Yep, 0.25. And so the point, though, what I'm trying to illustrate with all this is that we don't need to worry about how steep these things are or how far they go out. The only thing to really decide is this thing bigger than 1? Is the base bigger than 1 or less than 1? And if it's bigger than 1, right? And here you're looking at this and going, that looks just like a line. I'm going to graph it like a line. You're wrong, because when you zoom out far enough, look at that. It looks exactly like the curve that we've been drawing. So let's do a few problems that show up in the book that are very much like your homework problems. Number 2 says to graph the function. It doesn't write it as a function, but it says graph y equals 3 raised to the x. What I'm looking for is this, that you go, no, is that base, the base of that exponential function, bigger than or equal to 1? Bigger than or less than 1? And you say, well, 3 is bigger than 1. And so you think, okay, then it should, as we go this way, it should increase, right? It should shoot up. And so what I'm looking for is this. We also know exactly where it's going to go through the y-axis, right? Plug in a 0, you get out a 1. Okay, so we're going to label that point. And we're just going to do this. Pretty easy. Now, I do want one more thing. I would like one more point on this. You could choose whichever point you want. I don't care. Actually, I mean, it'll be nice, and you'll see why I'm going to choose this one. What's like the next easiest thing to plug in besides 0, almost to any function? It's 1, right? And what's really nice about this is 3 to the 1, you don't have to use your brain. You just get out that thing. And this would be a nice way of checking that you have the right picture. You'll notice I didn't bother to say, oh, wait, there's 1, that 3, that's actually as high as 2. I don't care. This is what it should look like, right? It's qualitatively accurate. It gets bigger as you go this way. You plug in a 1, and the thing you get out is bigger than 1. All right, that looks good. That's what I'm looking for. Go ahead and pause the video and try to graph this one. You should be thinking, okay, I have an exponential function. I have a base that is less than 1 because 1/6 is less than 1. So it should decay, right? And just making sure there's nothing funky going on. When I plug in a 0, I get out a 1. Yeah, okay. So when I plug in a 0, I get out a 1. and it's a decay, so it looks like this, and it shoots up when we go that way. Now, if you'd like, you could plug in any, I would like one more point on this, right? You could plug in 1, that would be cool. And when you plug in a 1, you get out a what? Well, that's easy, 1/6, right? And now I'm just going to double check myself. Like, is that an accurate graph? Yes, you plug in a 1. I know you get out a 1/6, and 1/6 is less than 1. So we're good to go. You could have, if you were so inclined, plugged in a -1 and said, oh, you plug in a -1 and you get out a 6. Why is that? Well, remember, it's that backwards deal, right? -1, we could think about that as flipping the fraction, raise it to a 1, it comes out to 6. Bunch of different ways of doing it, but that's the idea. Pause the video and try to do this on your own. Okay, I'm graphing an exponential function, and I could see that the base is between 0 and 1. And so this thing has to decay. And so it should look like this. And it should go through at 1, go through the y-axis at 1, because, and I'm going to double check that when I plug in a 0, yeah, there's nothing funky going on. Plug in a 0, get out a 1, boom. And now when I plug in a 1, I get out a 0.3. That looks good. That's what I'm looking for. The last kind of question you're going to have is to graph this thing. And this is not exactly the same as what we've been doing. And in fact, what I'm going to do is say, let's think about this as a function. And what we could do is say, man, this is, I know how to deal with 2 to the x, right? And if we had a g of x equals 2 to the x, we'd say, well, I know exactly what that guy looks like, right? Well, we've even done that in class, right? But we say the base is bigger than 1, so it does that. Boom, goes through here at 1. Bam, done. We plug in a 1, we get out a 2. And that's all we're looking for, right? That's 2 to the x. But now, well, this thing, it's as though you took this function and you've subtracted 1 off the input, right? Now, this would be different than, say, something like this, 2 to the x minus 1. That would be subtracting from the output of this function. And then we would expect, well, subtracting from the output would shift this entire thing down. But when you subtract from the input of a function, because that's what's going on right there, right? We're saying that you're taking the input, and instead of plugging in an x, you're plugging in an x minus 1. You could even see little, you could imagine little parentheses around there. And you could say, well, hold up, this function that we're trying to graph, the function that we want, it's as though you took your original function, that, and subtracted 1 from the input. You could see, like, yeah, that's exactly what that is. If you, instead of plugging in an x, if you plugged in an x plus 1, that would give you that. And so what do we know about subtracting from the inputs of functions? It shifts the graph. And when we subtract 1, it should shift it to the right by 1 unit. And so what should happen here is it should take both of these points, the thing that we want to graph, and I'll do this in green so it's not so bad. It should take this point and bring it over 1 unit. It should take this point and bring it over 1 unit. And everybody else should kind of follow suit, right? It should just look something like that. And that should be the f that we want to draw right there. F of x is 2x minus 1. And this is where that whole going through 1 right there kind of fails, right? And when you have a function a to the x, and it's just a to the x, then it doesn't matter what a you have. When you plug in a 0, you get out a 1. But in this case, it's pretty clear that when you plug in a 0 right into there, you don't get out a 1, right? And so this is a function you're trying to draw, and it goes through an axis. And so you need a label where it goes through the axis. And how do we do that? Well, we say, well, it's going through the y-axis. That means that the x value is 0. And so we'll say, all right, let's get this stuff out of the way first. And we could just say, okay, well, where does that occur? Well, let's plug in a 0 and see what we get out. So f of 0 is 2 to the 0 minus 1 is just 2 to the minus 1 is just 1/2. So it should go through here at 1/2. And that kind of makes sense, right? Because if you think about the red function, 2 to the x, when you plugged in a -1, you got 2 to the -1 is 1/2. And so he came out to 1/2 right there. And then when we shifted all of these points 1 unit to the right, it brought him over right to there. Okay. And so let's just kind of do it from the top. This is what I would, so the green function is what your thing should look like. And I've only, as of now, labeled 1 point. But I'm going to do it from the top to show you what I'm looking for all together here. So, okay. It says graph f of x equals 2 x minus 1. So I'm going to go, okay, this is an exponential function. Let's see. Is it going to grow or decay? Well, the base is 2, and so it's going to keep getting bigger and bigger as I plug in bigger numbers. It's going to blow up. Okay. So it does that. Boom. Easy. Done. Now we need to find a couple points. Well, let's plug in a 0. Plugging in a 0, I get, we just did this, but I'll do it again. 2, 0 minus 1 is the same as 2 to the minus 1, which is 1/2. So that's 1/2. So I plug in a 0 for x, I get out a 1/2. Okay. And I could realize that as, yeah, like we said before, and really that is the way I would think about this. It's like, well, wait a minute, it's just the regular function we had shifted over. Okay, cool. And now what we could do is plug in a 1. Plug in a 1, you get 2, 1 minus 1, 2 to the 0, 1. So we get out a 1 right there. And that would be perfectly fine right there. That's what we're looking for. But it's good to, I mean, it is very important to be able to see something like this, and you're not just plugging along the way that I did this, that you go, oh, that's a function that's been shifted. Like, you should immediately recognize that whenever you see a input being added or subtracted to. And now also, if you see an input being negative, you know now that that is a flip around, or a reflection around the y-axis. So the way you actually go to draw this might be a little bit different than that, but do have that shifting in your brain. Like, don't disregard that. So the homework will be chapter 12, section 2, page 525. 1 through 11, odd, and those are all just graphing, just like what we did. 21 is the last kind of graph that we just did. And then 21 asks you to find the domain of something. And when you do that one, remember how we think of domain is all allowable input values. Should not be a very hard one. And then it's 25 is the one very much like the last one we did. So good luck, and I will see you Monday.